Morning, everybody. How y'all doing?
Good.
Glad to hear. A couple brief reminders before we get started. Cursor. Today's Monday the 24th. Chapter 5 homework is currently due Wednesday the 26th at midnight, since we didn't have class on Friday. So in a second, we'll open up the floor to any questions you guys have about the Chapter 5 assignments. Additionally, as you're working on those over the next day or so, you remember that there is tutoring in here on Tuesdays and Thursdays. You guys can also come to get some help from physics major students. But we will also be able to talk about any questions you guys have on that assignment on Wednesday as well, since it's due at midnight. Main thing we're going to focus on in lecture this week is Chapter 6, which is about momentum and collisions, kind of a direct continuation from last week. And no matter how much time we spend on homework questions today, I want to at least begin Chapter 6 to make sure you've seen the formula for momentum and its definition, since the lab this week is about momentum and collisions. So there is lab this week. Do come to your normal time, and I think that's everything that you need to know for now. How you guys feeling, and what questions do you have about the homework that's due Wednesday?
Did you work out like question 7?
7. Yes.
That's
That's
what
what
I
I
worked
have on the board. So, 7 is an energy transformation question. Namely, the energy here is going to transform between 3 different forms at 3 different points in time. Here we have a spring-loaded projectile launcher. The spring is compressed to a certain degree. We don't know the spring constant, but we do know the amount of compression. And when that spring releases, it's going to fire the marble straight upwards. We are told the compression of the spring, the mass of the marble, and the distance that the marble is going to rise to after being fired vertically straight into the air. So, first question, as a reminder, these text prompts, you don't actually have to input a correct answer into these because WebAssign physically can't grade them. It's just going to give you a point for having anything there. So write the letter Q, free point. I do want to address it though because it talks about the energy transformations in this question, and understanding where the energy is going helps work the question. So in this initial state right here, while the spring is compressed and nothing is moving yet, what form of energy is present in the system at that point in time? Say again? Almost. There is potential, but the potential is in the spring because the spring has been compressed, like in the marble cannons. So if the beginning state is spring is compressed, nothing is moving, marble has not risen yet, then initially you'd have EP, elastic potential energy. Elastic. Now, what form of energy do you have after the mechanism's been triggered and the spring goes back to normal and the marble now has velocity and is about to start rising? The whole point of spring-loaded launchers like this is to give I just said it wrong, is to give KE to the projectiles. So, when the spring is compressed, the system has EPE. When the spring goes back to normal, all that EPE is going to become KE in the marble. So, stage 1 here is EPE. Stage B here, goes to K and B, is all the energy is in KE. The spring has gone back to normal. All the energy that's stored in it is now in the marble. The marble has a launch velocity. And then even further down, what energy do you have after the marble has risen, for me, 24 meters into the air and stops for a second? GB, yes. So we're basically transforming between every single form of energy we've talked about in here. We start with EPE, becomes KE, and then eventually becomes GPE. So question A is just asking about all the steps of that transformation. Understanding what form the energy is in at each time will help with the next two parts. Part B, ignoring all resistant forces, determine the spring constant of the spring. To do that, I have listed our variables over here as usual. You're given the mass of the marble, you're given the compression of the spring, and you're given the height the marble eventually rises to. Now, there's 3 stages to this one. There's the very beginning stage where you have EPE, there's the launch stage where you have KE, and then there's the final stage, 24 meters in the air, where you have GPE. To figure out what the spring constant of the spring is, we're going to have to compare the energy total of that initial stage to one of the other 2 stages. And we don't actually know enough about the launching velocity stage to really use that one yet. So what I've done on the board is I'm comparing the initial EPE to the final GPE at that last point where you're 24 meters in the air. Again, conservation of energy. However much energy is in the system must remain constant. So our initial stage, we have EPE compressed in the spring. And our final stage, for this one I'm treating the final as all the way risen up into the air. We would have GPE based on the height at that point. We were specifically told there's no friction here, so there's no work not conserved. It's just a direct transformation from EPE to GPE. EPE's formula, 1/2 K times delta X squared. We do know the spring's compression. We're going to solve for spring constant. That's equal to the GPE formula, which is marble's mass times the absolute value of 9.8 times the height that you rise to. Doing this, and you should get a fairly large spring constant. Excuse me. Questions about part B? Okay. Part C is pretty similar, except now that we know spring constant, we're going to look at that middle phase where the energy is in the kinetic form to figure out the top speed it was moving at the second it launched. That's the stage where all the EPE is turned into KE inside of the marble. And technically, you can compare that KE at that moment in time to either the initial EPE or the final GPE. There's functionally no difference in terms of the energy level. I've chosen here to compare the initial EPE to the KE of the launch. So, same basic starting point. Mechanical energy initial equals mechanical energy final plus work not conserved. I'm still choosing to treat the EPE stage as the initial, and now I'm treating the KE stage as the final instead. We're looking at a different point in time and just arbitrarily labeling it the final one. So this is instead the point where the marble is moving at top speed right as it's beginning to launch. And once again, no friction, no work not conserved. To do this, you do need to get a correct answer for your spring constant first.
The second equation is solving for speed, right?
Say again?
Yes, solving for velocity. How's this one feel? Did that address your original concerns?
Yes.
Any other homework related questions at the moment? Yes?
Can you do 6?
6. Yes. I wrote which one that is. Ah. So, the physical setup for 6 looks exactly like the Atwood's machines that we did in some previous examples a couple of weeks ago. But now we're going to be analyzing it through the lens of energy as opposed to just kinematics and tension. So we're using energy problems to work this one. 2 blocks are connected by a light string. You're not originally told the masses in the beginning, that's fine. But we do know that M2 is smaller than M1. M1 is going to fall some distance. As it does so, at the beginning, M1 has some amount of GPE that's going to transform into KE across the whole system as things start moving. The first thing that we're asked is, assuming M1 is bigger than M2, find an expression for the speed of M1 just as it reaches the floor. And this, what it's getting at here, much like the previous Atwood's machine questions we looked at a couple of weeks ago, these 2 objects are physically tied together. They're going to have the same final speed. So that's unchanged from when we looked at similar questions in the past. But now we're doing it through the lens of energy instead of just kinematics. So to do so with energy, we need to analyze what energy forms are present in the beginning stage, which is what's shown here before things start moving, and the final stage, right as M1 is at its fastest and about to hit the floor. We're going to pause time before it actually hits it. We don't know how much speed it's going to lose in the crash. We're freezing time right before it touches down. So, in the initial stage, in this picture, what form of energy does the system have? In the initial stage, is anything moving yet? No, so there's no KE in the beginning. Additionally, M2 is on the floor, so it doesn't have any GPE. The only energy present in this system before you let it go and before things start moving naturally is the GPE in M1. It's the only form of energy present at the beginning of this one before things start happening. So for our initial energy total, it's just going to be GPE 1 initial. The GPE of mass 1 here in the initial time frame. So that's the initial stage. The final stage, I'll actually draw a separate picture for that. In the final stage, M1 will descend, it's going to lose its GPE. Meanwhile, M2 will ascend and gain GPE. So there's going to still be GPE present in the end state, it's just now M2 has it. And it's going to have a different amount since it has less mass. So, beginning to write out things for the endpoint, I'm going to write in GPE of object 2 final. Additionally though, that's not the only form of energy that's present here because both objects are moving at this point. So both objects, they're tied together, they have the same magnitude of velocity, they will both have kinetic energy here. So both objects, 1 and 2, have some amount of KE final right here at the end. Again, this is before M1 hits the floor. We're freezing time right before that happens. The collision makes it harder. And if we're ignoring friction, which the question does tell us to do, that's all the forms of energy that are present at the beginning versus at the end. And the goal of this first part is just take that premise, don't plug in any numbers, rearrange it and solve it for VF. Now, for one, WebAssign is always kind of finicky about inputting equation answers. So I'm going to show you this one and you'll have the comparison to check your work against to make sure you're inputting it right. And to show where that comes from, formula for GPE is this is specifically the GPE of object 1. So that's mass 1 that goes in there. MGH equals object 2's final GPE, excuse me. So that's M2 G times H. The mass is different there. Plus 1/2 M1 times VF squared plus 1/2 M2 times VF squared. So I'm not plugging in any numbers, I'm just plugging in the formulas and labeling the variables. The goal is to solve for V final equals, and thankfully, since the two objects are tied together, they will have the same velocity. It's the same VF term in both of these different KEs. The masses are different, but it's the same VF each time. So it's not two different variables, it's just one. It's in two places at once. That means that we can use a distributive property to combine these two statements, which will make life easier for us. So right now I'm just combining this, boiling this down, and showing where the formula that is the answer comes from. I'm going to move this GPE term to the left since it doesn't have a V in it. So that's going to be, let me find a marker with blank in it. And 1 GH minus M2 GH equals 1/2, using the distributive property, M1 plus M2 times VF squared. Both of the kinetic energy terms have the same 1/2 and the same VF squared attached. So I can distribute both of those out and turn it into this. What this means is, since they're moving at the same speed, there's basically one kinetic energy shared across both of them that is powering their combined mass, since they're moving at the same speed. And at this point, it's just a matter of simplifying this down to get to VF equals. Now we'll form that, yes. And we'll show another step of that process. These two terms have the same GH in them, so we can perform the distributive property the same way. M1 minus M2 times GH equals 1/2 times times the sum of the masses times Vf squared. Multiply both sides by 2, divide both sides by m1 plus m2. And you'll end up at the same point as the version on screen. Last step would be the square root. It's a lot of work, but it does give you the velocity formula. It asks for this first so that you can then use it to actually solve for that velocity. We've done something similar in lab before.
The G would be 9.8, right?
Correct. So I'd say A is the hardest part of this question. It's got the most algebra, there's no numbers to simplify, it's just algebra. But once you get to this point, B and C are just plug numbers in to the formula that you just found. B specifically says, plug in these two masses and this for H, figure out how fast they're moving after they've fallen that distance. C basically just has you change the H term, because at that point the objects will have fallen. It's asking about the velocity after they've only fallen so much of that distance. So you plug in a different H term. How's this one feel?
Wait, what did you say algebra for C?
C, so part B is what gives you the numbers for M1, M2, and for H,
Yeah.
and you take those numbers and put them in here.
Yeah.
C is just having you alter the H term from up here,
Oh.
because it's asking what is the speed when they've fallen this distance instead of falling the full distance.
Okay.
So what is the speed partway through the transition? Questions, concerns, etc.? Any other questions from this one in your minds at the moment? Sorry?
Work on this specific one.
Well, first, how does this one feel now? Okay. Next, anything else?
And we could do 3 and 9.
3 and 9. 3. Yes. And we'll need to erase something. I'm gonna leave this up on, I'm gonna leave 6 up on the board. So 3, we have a bullet moving very fast being lodged in a tree trunk. Actually pretty similar to a different example we're going to work soon, but using momentum instead. You're given the mass of the bullet, its launch speed, its initial velocity before it makes impact, and then how far it is buried into the tree trunk. Part A, use work and energy. When it says use work and energy considerations, that just means do this with energy formulas rather than the old formulas that we would have historically used. Because we could answer this using Newton's laws and kinematics and the stuff we did at the beginning of the course. The point is just try it out using energy to see how it works. So that's how I'm going to show it to you. So using work and energy, find the average force that stops the bullet. Once the bullet enters the wood will exert some force on it to slow it down. And that's the mark. Where's the one I just had? There. Now, when the projectile strikes the tree stump, stump will exert some force upon the projectile as it moves some distance into the log. Force times distance is the work formula. Coming into the log, the projectile has some amount of energy, and it's going to lose that energy as the log exerts a frictional force as it moves some distance into the wood. So this is the formula we're going to use for the first part. The force is actually the force you're going to solve for, because this is the force of friction that does the work to slow down the projectile. This is the distance that force will be applied over, so that will be the displacement. That means we just need to figure out, in order to solve for that force, how much work does the log do? We need to figure out how much energy the bullet has initially, because the log needs to do enough work to take all that energy away. What form of energy does the projectile have initially before it strikes the log? The object is moving, it has mass and velocity, therefore it should have some initial amount of kinetic energy that friction wants to completely remove. So there's actually not going to be any mechanical energy left. Friction is going to work to take away and absorb all of that KE. So, 1/2 times the object's mass, which is a very small number of grams, times its velocity. This number will be different for everyone. That will equal the force that friction exerts times the distance that it is buried into the wood. Oh, that's centimeters. Excuse me. And this will tell you the force of friction that stops the projectile. I'll check the answer to make sure this works. Yes. Yes. Without factoring sig figs, without rounding much, my unedited answer is 22,687.5 newtons, which, counting sig figs, would round up to 22,700. So that's force to stop the projectile. Next, assuming the frictional force is constant, determine how much time passes between the moment. Wait, that is power. Oh, I see. Hold on. Take a minute. I need to check something first to make sure I'm not missing something. Bless you. Multiply that by the initial velocity. Divide that by All right. Disclaimer, there's something kind of weird going on with 3B. And I could figure out what the original author wanted, but I have a rule. If it takes me longer than a couple of minutes to get the absolute correct answer, then it's not a good problem for you guys. So what I'm going to do is I'm going to tweak the point values so that part B is worth 0 points. Because I'm officially ruling this one as weird. And too weird for you guys to have to worry about. Because I feel like there's a piece of information missing. I could figure it out, but again, if it takes me longer than 2 minutes, it's not a good question for you guys. So, what I'm going to do is, within part 3, on your version, when you look at it, you should see how many points each part is worth. I'm going to make part B worth 0 points. So no matter what you do for it, it doesn't affect your eventual score. I don't want to remove the question completely because some of you may already have that one done. But I also don't want to penalize people for this one just being odd and possibly poorly written. So that will change part number 3 from being worth 2 points to just being worth 1 point. Questions, concerns? Okay, I'm glad you asked because my first assumption didn't work and it's taking me a minute to figure that one out. You said 9 as well? All right, 9. All right. Come on. Ignore this. I'm just going to do the work for 9 in red right here. 9 is a power question. And to use it, to do it, velocity, power, watts. You're going to need one of the 2 formulas for power. In this particular question, you've been told that an automobile is moving at constant speed and the power developed by the engine is used to overcome the friction slowing it down. This is true for all cars that are driving at constant velocity, like you can on cruise control. The force forwards from the engine must equal the force backwards from friction in order to keep the car moving at constant speed. We are told the horsepower of the engine, that is its power, it's just in the wrong unit. We are told to calculate the total frictional force acting on the car when the car is moving at some velocity. That's 2 of the 3 parts of this particular version of the power formula. Power equals force times velocity. To figure this one out, you need to convert however many horsepowers you were given into watts. Take your velocity, plug it in for V, and then solve for this force. This force would technically be the force the engine is exerting forwards to move the car at that speed. But, conversely, third law of pairs, the value of friction slowing you down would need to be the same thing in order for the car to be moving at constant speed. So, this formula, solve for the force of the engine, that would be the same thing as the force of friction slowing you down. The one catch is to make sure you convert horsepowers into watts, which is why the question gives you that conversion. This one feel a little bit better? Any other issues with this? Okay. I'm hoping that this assignment is feeling a little bit better. As a reminder, it is due Wednesday, so you do have tonight, tomorrow, and we have lecture on Wednesday to further discuss it more if need be. At this point, I do want to switch gears a bit and make sure that we've introduced momentum ahead of lab today. Namely the formula, because you're using the formula at least. So, Chapter 6 will be about momentum and collisions. We're going to define momentum and its formula. In doing so, the definition for momentum should feel very familiar. In fact, you might wonder, what is even the difference between momentum, kinetic energy, and inertia? Why do we treat them all as different things? And that's going to be something that I'm explaining and helping to make sense in your brains over the next couple of days. The textbook definition of momentum, we're going to start with the boring one, and we're going to make it make more sense in a minute. Momentum is a quantity related to the motion of an object with matter. An object needs to have both mass and velocity in order to have momentum. According to the formula, momentum, the P is the momentum. There's not a very good reason why. Momentum is equal to an object's mass times its velocity. Whenever an object is moving, as long as the object has mass and is moving, it has some amount of momentum compelling it to keep moving at the same speed in the same direction. This is the part where this may start to sound familiar. That is the formula up top. Technically, that is not a lowercase English p, it is a lowercase Greek rho. As a result, you may hear me call it rho. I may say rho equals mv, or I'll refer to it as rho in some other formulas. I'm just informing you, it is momentum. You're allowed to call it p. You're allowed to type a normal letter p. There's not a big difference between lowercase rho and lowercase p. I'm just letting you know for when I say that. If it helps, you can call it rho-mentum if it makes more sense for the formula. And to try to summarize what momentum is in something that's a little bit easier to digest, momentum can be thought of as a measurement of how difficult it is to stop an object that is moving. The more momentum something has, the physically more difficult it is to bring it to a halt. Now you can increase an object's momentum by either making it faster. If something is faster, it's definitely harder to stop, like slamming on the brakes of your car. It takes less effort to stop if you're moving slowly than it does when you're moving fast. But additionally, an object's mass is also a factor in its momentum. So if you have an object that's moving very slowly, but it still has a lot of mass, think a train pulling into the station. When they're entering the station, they don't want to move very quickly. They might just move at like 1 meter per second, but a train has a lot of mass between the engine and all the other cars. So even though it's moving very slowly, if you, a normal human, were walking next to it and put your hand on it to try to stop the train, even if it's just moving at 1 meter per second, how easy would that be? It would not. Do not try to stop trains. The train is made of metal, it has a lot of mass. It is still very hard to stop, even when it is moving very slowly. Momentum is a metric for how hard something is, how difficult something is to stop. This does mean that you do have to be moving in order to have momentum. The formula does dictate you need a non-zero velocity. If velocity is zero, then you just have no momentum, and you're very easy to stop because you're already stopped. Questions so far? Okay. This is a new unit. It's a new formula. Momentum's a new unit, so time for the list of things about that unit that you should know. The variable rho is the unit, the variable, for momentum. Things to note, momentum is a vector. And its units are kilogram meters per second. It does not have its own dedicated unit with its own name. The unit for momentum is just mass times velocity. I assume this is the case because most of what Western science uses for momentum historically also came from Newton. Like, he got famous for writing down the laws of motion, but he also got famous for writing down this. And since his name is already on the unit for force, they didn't have another name to put on this. So, unit for momentum is just kilogram meters per second. It's a bit of a mouthful, but you can derive it just from the formula. Using that formula, pop quiz. There's 4 situations currently on the board. Which one has the most momentum in it? One vote for D. Any other guesses? All right, I'll just go down the list. How much momentum does a stationary object have? 0. Velocity is 0, then momentum is also 0. So this building, again, it's already stopped, so it's very easy to keep stopped. The bullet has a mass of 10 grams and it's moving at 1,000 meters per second, which is very quick, but the formula does call for kilograms. So 0.01 kilograms times 1,000 is only 10 kilogram meters per second of momentum. The dog, all of its units are in the correct form, so 25 times 10 is 250. And the car, 2,000 kilograms moving at 1 centimeter per second, so that would convert to 0.01 meters per second. 0.01 times 2,000 is 20 kilogram meters per second. So the dog wins, actually, in terms of the entity here that is most difficult to stop. It literally requires the exact combination of both mass and velocity working together. Since there isn't a squared term here, one is not more important than the other. All right, I'm gonna go back to the momentum slide for a second. Now, momentum can be weird because it's similar to a couple of other things we've already talked about. One of them being kinetic energy. Because if you have kinetic energy, you have a mass moving at a velocity, then you would also have momentum at the same time. Because you use the same mass and same velocity to find the two different numbers. Kinetic energy and momentum are very similar. If you have one, you have the other, and both compel objects to keep moving at a certain speed. They exist simultaneously. It's not a case of do you have one or the other. If you have one, you also have the other. And the reason we keep track of both separately is because of the differences between them. The primary difference being momentum's a vector. Is kinetic energy a vector? No, no form of energy is. That's because energy doesn't actually care what direction something is moving in. It just cares that something is moving. If you give a child a bunch of candy, they have a bunch of energy and they don't really care what direction they're running in, they're just gonna run. Whereas momentum, since it is a vector, it does care about the direction. Then the KE formula, the velocity gets squared. That's the reason that the vector goes away. But in the momentum formula, it's just velocity times a scalar, so the direction doesn't vanish. Momentum inherits the direction from the velocity in the formula, meaning that if you're moving to the right, your momentum wants you to keep moving to the right, whereas your energy doesn't care. This becomes more apparent when we start examining collisions, which is the primary sort of problem that we're going to be using with momentum. And it's what we're going to be studying in lab this week. The drawing I had past couple of sessions is gone now. Very quick, very small doodle. Let's say you fire a cannonball at a brick wall. I used to watch a lot of Mythbusters. That cannonball is moving to the right. It has both kinetic energy and momentum because it has mass and velocity. And when it hits the brick wall, it's going to slow down. It might even stop. So it's going to lose some kinetic energy and some momentum because it's slowing down. Now, the kinetic energy that the cannonball loses could turn into different forms. It could enter the bricks, it could enter the sound, it could enter the air as sound. It could turn into heat in the crash, and the energy at no point cares about what direction it's moving in. The sound in the crash is going to echo out in all directions. The bricks from the crash are going to fire away in all sorts of different directions. The energy doesn't care. Different forms, different directions, it doesn't matter. Momentum is a vector, cares about the direction, and it only has one form it can occupy. Whereas energy is conserved as long as it still exists in some form. We're going to be studying how momentum is conserved in a collision, but it only has one form it can occupy, and that's momentum. Momentum doesn't transform into other forms, it's always momentum. And it's going to want to keep pointing in the same direction. That's the reason why the cannonball keeps moving to the right through the wall. Its momentum compels it to keep moving to the right, even though its kinetic energy doesn't care. It is kind of weird distinguishing them. We're going to be using both KE and momentum simultaneously. We're going to be studying the differences. I'm going to make sure that they make sense. I promise. Sorry. Main things to know about this before going into lab this week is that formula, keeping in mind that momentum is a vector and that, like how energy is conserved, momentum is also always conserved in an interaction. It can change what object has it, but it is also conserved. And that's going to be one of the things we study in lab this week. Questions? All right. That's it for everything I wanted to cover for right now. I'll leave this up if you want to keep copying. But then you don't really have to do anything with this right now. It's just setting the stage for lab this week. Let me know if you need anything as you work on homework or what have you. I'll see you for either lab this afternoon or for lecture on Wednesday. Thank you and have a wonderful